So my name is Martin from Mohrenschildt. I'm the chair of the Department of Computing and Software. Just give short about myself. So I'm here at McMaster like 16 years. Originally actually started pure maths, then became more and more applied. So in the meantime, I'm an engineer. I teach control, robotics, game design, so I have a virtual reality simulator, which you also might have seen. And today I just talk to you about, in general, about computing, but in order to make it a little bit interesting, I tell the story about this robot, and then give in between some comments about computing, what to choose, and so on. Now my general question, who's interested in computer science? So there are very few, the other ones are mainly software or mechatronics or things like this. So just that they have an idea. So I talk about all of these kind of different things, and if you have any questions, just interrupt me. So let's just start out with the general idea. So I have this this thing here. It's quite a nice toy. I actually have even a more sophisticated one, but this one you actually see the stuff happening. So that's a very simple robot. It's simple. It's like $2,500, so it's not really a toy. It has a computer on it and so on. What I do is explain you how this thing works and use this as a story to explain what the role of software is, the different programs and things like this. So let's have a look at this. That's really a very typical engineering system. And so what you have is, so we have this robot, and we actually typically have things which sense the environment, so sensors, and we have things which act to the environment, the actuators. We have a computer on it which makes a decision. Now this one is actually wireless, so most of the decisions are actually happening on my laptop over there. That's just for convenience and out of choice. So it has a local computer on there, but all the control is happening on my laptop. So let's just go shortly through the sensors. It has ultrasonic, infrared sensors. And then there's a motor. So you see from the pictures, it's not everybody can see this stuff here, but you see these sensors just lined around just everywhere, and down there the motor and so on. Let's just go have a short look at these sensors. The first one is an ultrasonic one. So there's a speaker and a microphone. What it does, it works like a bat. So it plays out a sound. The sound reflects off the wall. It comes back. So it plays out the sound on one side, records it on the other side, speed of sound, your time, how long it takes, and you can compute the distance. Okay? So that's distribution. So this is not, it's not perfect kind of measurement. I have a more sophisticated one, which actually has a laser rangefinder. But the laser rangefinder then costs just a laser rangefinder as much as this entire robot. It works quite well. So what you do is in the software, you send it out, you time, and you record it back on the other side. But now, since this is such a common task, what they actually do is, on back of this thing, there is actually a small computer. Okay, so there's a small computer which takes care of all of these computations, and my main computer just links to this computer over a small communication cable in order to get the information. This brings me to my first point. Most people think about software, they think about the PC. Now the PC is just the smallest amount of software which is around in this world. You all know Intel, a famous company. They make the CPUs which are inside your computer. They make the vast majority of their money, like in the order of 90% of their money, of CPUs which are not inside the PC. Just go home and count your computers. You have an MP3 player, a cell phone, a satellite receiver, a television. If you buy a modern laundry machine, I don't know how many people do laundry, but if you buy a modern laundry machine, they're actually computer controlled in the meantime. You just have so many computers at home and perhaps one or two PCs. So you have to think about this. The computers are just everywhere. Most of them are what they label embedded, so there's not a screen. They're just hidden away somewhere, but they all run software. So somebody has to write the software. And you can actually not even imagine modern life anymore without all of these computers. Like in a car, you would have 10, 20 computers. They're just absolutely everywhere. And the interesting thing is that it became much cheaper to take an off-the-shelf computer, since they're just a single chip now, very cheap, you can buy them for $5, $6, and write the software on top of it. since then you can change it, update it, and all of this kind of stuff. So the trend is that all the intellectual property, with the intellectual property I mean all the development which a company has, actually goes inside the software. It is not inside building custom hardware. That's really the trend, and it goes further and further. If you take your cell phone, oh yeah, now the numbers I have are already 2-3 years old, but the cell phone has about two CPUs, there's some special CPUs in there, and 700 kilobytes, so there has to be old things. I mean, we're now like in a megabyte range of software. All the thing is there. If you go to a phone company, you know what the phone company makes money off. They're not making money off by putting wires into your house. They're making money off selling you services, you know, call answer, call waiting, and all of this. You know what it is, software. Your telephone at home, your cell phone too, but your telephone at home is just directly connected just to a machine. So you have to just imagine, computers are everywhere, and it became so cheap that even on such a small sensor, you can just put one behind it. So this one allows us to do these measurements. Try not to run over you. Now we have a short range one, so this ultrasonic one works quite well on a long range, but we also have a short range one. They're infrared. It's essentially the same what you have in your remote control. You have one sending out an infrared, the other one receiving it, so now we're talking speed of light. This actually works quite well on the short distance. They're using infrared, since you don't want interference with your normal light. They work in the like 2 meter range. The ultrasonic is 10 meter range. They work in the 2 meter range, and are 5 to 50 centimeter range. So they're quite a bit more precise for the local one. So you can do general planning and so on. There are actually another two on there which I didn't even mention. These ones, that's the same stuff you find on your alarm system. They detect heat when a human is approaching it, but I don't even have them on my sensors. Now the next thing is interesting are these things which are on top here, these small things. And these things are called encoders. So that's also part of a sensor. Now what is an encoder? I actually have to know very precisely how this wheel is moving. You know, I want to know very precisely how it's moving. Now this is done technologically, it's actually quite ingenious. What you have is on the wheel you have a disc like this. And there are LEDs which go across. You see this? So there's a whole bunch of LEDs. The disc rotates, and on the other side I have a light sensitive array which detects it. This one is actually a 10-bit one, so it has 10 LEDs. And you all know what this is. That's a binary code. You know, it goes 0, 1, 0, 1. The next one are the 2s. The next one are the 4s, and so on. So when I read out the light, I can immediately read out the binary code of where my wheel is. So this allows to see the position of the wheel. But they're a little bit more clever than this. They actually have 2 of these arrays, even I don't show them in the picture, and they have to just slightly offset. So now when you take the 2 channels, if the one channel, you know, you can have 2 things, so if it's coming from the left, then this channel will have a tick before this channel, and if it comes from the other side, this channel will go high before the other channel, so I actually can even see if it's turning left or right very fast. Okay? Now, once I have this kind of information, I can very easily, so I can know the position, so I can compute the speed, I can compute the acceleration, and all of this kind of stuff. Now, obviously, again, there's a piece of software running. There's a chip on there, so it actually sends over a serial connection, so there's a small computer on there again, over a small connection disk. You see there's just 4 wires there, which send this information. I mean, 2 wires you need already to do the power, so the information just goes over 2 wires. Okay. Again, small computer on there. Okay, so now we know how our wheels are turning. The next thing what we have to do is we actually have to move this motor the correct way. You don't see the motor. There are 2 motors underneath there. Okay, so they turn these wires. Now a motor are quite interesting. I mean, a motor, you can take a battery, just hold the battery to the motor, and it just turns, but you have no control over it. So how can you control the speed of the motor? What you do is you connect it, disconnect it, connect it, disconnect it, and the amount of time you have it connected tells you how much energy you actually put into the motor. So the idea is that, you know, you do it 20% of the time. So you're putting a certain amount of time, energy in it. You see, I'm connecting it longer, and I'm connecting it even longer, so I can control how much energy I put in it. This is, by the way, the same way how the dimming of the lights in the buildings work. You know, they work with 110 volt. The only thing is they switch it on and off, on and off, and on and off. When it's more off than on, then it's darker. And they do it so fast that your eyes can't see it. So it's just a question of how much energy you put in it. So again, we have on our program, we can control and say how much energy we put into each of the motors. Okay? So now goes that we actually have to start putting this stuff together. And that's a very typical thing. Now here I think it's a good point to just talk about, so now we went away from the hardware stuff and we are interested more in the software. Now if you study, today things are actually quite interdisciplinary. You know, if you build an engineering product, you actually have to communicate with a lot of different things. An engineering product is not something one person will develop. And the key thing in order to be able to do this is to be able to communicate with the other engineers. You see, I talked about mechanical properties. I mean, there's a physical thing, mechanical thing. There's some electrical stuff happening, and there's software happening. And if you build this for a real system, I mean, it might be a car, you actually need specialists who really know about the mechanicals. Let's take the ABS brakes of a car. You know, brakes are not trivial. You have to know about the materials, about the heater. So that's more a mechanical thing. You need somebody to build the electronics on the car. That's more an electrical thing. But at the end, all is controlled with software. And you have to be absolutely sure, by the way, it works correctly. That's another thing we have to talk about. So engineering is a team discipline. And what the key thing to do is you have to be able to communicate with other people. You know? Since all other engineers, everybody speaks a different language. It's the same thing like you know, if you go to different countries that speak a different language, you have to be able to work on a team, you have to be able to communicate. And how can you understand this? You have to be able to communicate. Now, this is actually, in my opinion, not only in my opinion, one of the key things to get a good job. You know all this story about a computer geek, you know, the computer geek in the company who cannot talk with anybody else. In some sense, he's actually not very valuable to the company since, you know, the management or the other people come to him and say, we need this, and he does not understand what they want, and he talks about interfaces and, you know, uses his buzzwords, and they do not know what he's talking about. So if you want to go, computing as a service, you cannot imagine, there's nearly no branch anymore where you do not use a computer. You know, from library to psychology to forensic to engineering to civil to mechanical, everybody has a computer. And by the way, either you're the one who understands how the computer works or you're the one who is using it, you will not get by the computer. There's no way to get in by the computer. It's just absolutely everywhere. You can just count it, you know, how many computers are even, there's a computer in this camera for sure too. It's just absolutely everywhere. So what can you do? If you want a good job and not to be the computer geek, what you actually really should be able to do is you should learn the language of somebody who uses the computer. This is especially interesting for people doing computer science, since in a computer science degree, you can do a minor at the same time while you do your main degree of study. In engineering, it's a little bit more difficult, since due to the government requirements, or yeah, I call it government requirements, there are certain courses which are prescribed on you. But still, if you take mechatronics engineering, for example, mechatronics being a mixture between electrical, software, and computer, you learn the language of an electrical, you learn the language of a mechanical, you learn your software. So when you're in a team building some control system, you can actually communicate with the other ones. Same thing in computer science. I mean, you study computer science, but most of you don't want to end up sitting, you know, that's the picture. What does a software engineer, what does a computer scientist do? Most people think, oh, he's sitting in a cubicle, you know, day and night and hacking some code. That's very far from the truth. It's actually your own choice, or your own thing, what you will be doing when you're a software person. I give it to you like this. I mean, so there are two things. You want to be able to speak the language of the other people. So let's say you really love psychology. I pick psychology now. So we don't believe then they need computers. So you do a minor in psychology, and I guarantee you will get a very good job related to psychology, much more likely than when you just study psychology, by the way. Since you know something which they do not understand, which is the computing part, but they need it. but you talk their language. So they can come to you and say, oh, I really need a system which does this and this. So you go to the technological people, the technology people, the geeks who sit around, I mean, nothing against geeks, sit around and hack stuff, and you can tell them what to build. So the one who can communicate around is actually the key thing. In engineering, it's really, really important. Now the other question would be, what does a software engineer actually do? You know, he's not doing the code. And my favorite example to explain it is like this, you know. What does a civil engineer do? We all know a civil engineer is not standing on the construction site building a house. What a civil engineer does, he does plans. Most of you saw these plans. So this is, by the way, his language. That's his language, how he communicates with his peers and the people who actually build the house, makes these plans. He approves them, he signs them, gives them out, and somebody builds it. So now the electrical engineer, it's the same thing. An electrical engineer has circuit plans. Most of you know what I'm talking about. He's not sitting there, you know, soldering stuff together. He designs the circuit plans, gives it to a factory, which might be, by the way, overseas, and they build it. But it's still designed here in Canada. A mechanical engineer, the same thing. A mechanical engineer is not standing in a shop welding. You know, he does drawings, his language. So now you see where I'm going. A software engineer is not the one who's sitting in the cubicle hacking the code. He's the one who does some documents, which is then given to other people to code it. The interesting thing is that software engineering is relatively new. Computer science, the same thing. So most of you, I'm quite sure everybody of you, did never even see a document. You know, civil engineering is ancient. Then came mechanical, then came electrical. So it has a long history in the culture, so people quite well understand what they do. In software, this is quite new. But I'm quite sure you understand, you can get the message behind it. And since we're there, there's another thing which is very important. When you build control systems like this, you want to move something around, trial and error is also not an acceptable thing. Now my favorite story goes with this, you know, in old Egypt when they were building pyramids, you know, they put a lot of money into a pyramid, I mean labor. If they built a pyramid and this pyramid was not holding, I mean this building was not holding, you know what happened. The engineer would just get his head cut off. I mean, so they better developed a good way of developing, building buildings so they don't fall, you know, don't fall down. Same thing for civil engineers, later came the mechanical engineers. I mean, when you're driving on a car and you're going around the turn and the tire falls off, you know, the electrical engineer who designed this tire nuts and everything is in big trouble. Now, it's quite interesting, since in software, now most of you wrote some program. Who wrote ever a program which is longer than 5 lines which worked the first time? You know how you do programs. You write something, then you try it out. You write it, you try it out. But this is quite often absolutely not acceptable. It's not acceptable, especially when you write a software which controls an airplane landing. I mean, you cannot sit on the airplane and say, oh, let's try where it crashed. Let's change some lines of code. You need a completely different way of approaching this. And software is incredibly complex. And the interesting thing on software is that, you know, a mechanical system, how do you test it? You know, you build a table, you knock it a little bit here, you say, ah, it looks stable to me. You look at it on the other side, it's stable. Now, quite sure when you knock in the middle, it will not tip over since you tested it on both sides. Software is completely different. If you do software, it works for all values except for 11.3975777 if statements. So you cannot just test it here or here or here and say it works for all the time. So you need a completely different methodology to develop it. And this is actually what you learn as a software engineer or as a computer scientist. We do not teach you programming languages. We actually do not really care very much about programming languages. And how I explain is, you know, at the moment it's very popular Java. When you graduate, it might be cappuccino. I'm just making this up, it's a joke. Yeah, it's absolutely irrelevant. It's absolutely irrelevant what the programming language is. It is about the basic principles on how to write software, how to design something, you know, to decompose it in small things, and to be sure when you write it, it's actually working. Okay, so now we go back to this one here. So we have a typical situation, so we have our sensors, and we have our actuators, and in the middle we have to do the control. So we measure environment, we have to do some computation, and then we react to the environment, we measure again, so we get this typical control loop. It's a very traditional engineering picture. They did this already for steam locomotives. It's a very old style of thing. So what you do is, you actually say where I want to go, where I am, and then you take the difference, and then I get the error. So the goal of the software is to minimize the error. Okay. That's really how the software works on there. So how do we do this? Oh, I should actually show you. Let's just do this one here. Yeah, I should actually show you the sensors working. I nearly forgot about this one. And now I'm getting one. See that it connects. I was too fast. Let's just wait a second here. There we are. So I wrote it in a simple ASCII interface. So you just see numbers running around. What you see is position X, Y, and heading. That's the typical orientation, X, Y, and the rotation on it. We have these ultrasonic ones. You see he's picking up about you here, since that's why it's not 255. You see me, when I go in here, it will detect me here. You see this? I'm going here, it will detect me there. So there I'm in, that's ultra. And the other ones here, so I can show you, when I go around, you see essentially the value is changing. You see this, how I'm going? You see it? Next one. Next one. So you just see the values changing as I go around. Now, these are actually computed encoder readings. So when I start pushing this thing, you see how it starts computing. When I turn it, it changes the angle. This angle is in radian, not in degree. But you see it. So here it's like close to 2 pi. Pi is 3.1. So the thing that goes the other way around. And move it with the position. And now I do a very risky thing. I will actually move it here on the table, and I hope it will not fall down. So I can actually give it even a go, and then it will just move on a straight line. Moving on a straight line, this is actually not easy to do. It's much more difficult than you might think. How do I get this thing to move on a straight line? Now, these things, I mean, essentially, you would say, oh, if I get both tires turning exactly the same way, it would go on a straight line. That's not perfect, but now the problem is, I put some power to this motor. Now, how much power should I put to the other motor? The motors will not be 100% the same. So the idea what I'm doing is, I'm putting power to one motor to make one wheel rotate at the desired speed, and then I'm taking the other motor and try to match the speed. Since I can always see, I measure the speed on the one encoder, I can measure the speed here. If I'm a little bit too fast, I slow it down. If I'm a little bit too slow, I start speeding it up. That's how I get this thing to move on a straight line. So the first thing, I have one motor. I say I want it to run on a certain speed. If it's running faster than the speed I want, I make it slower. If it's slower, I make it faster. And then I take the other motor and match the speed of this motor with this motor. This happens about 60 times per second in order to be able to do this. So this brings us to the other idea of control. The problem is I'm running out of time. Let me give you this, I can give you this short. You're trying to match the thing. Now the thing what you get with it, you can try this yourself. I think that's still interesting enough. Now, what you normally want is, you want this thing to react very fast, be very precise. But you have a trade-off. That's a typical thing in engineering. When I want to move this from here to here, if I do it fast, I will have to correct my position. If I do it very slowly, I will hit the position very correctly, but I'm very slow. So you get the idea. You always have a trade-off. When you do it very fast, you might overshoot and you have to correct. There's nothing around it. You cannot go around this. That's physics. If I do it very slowly, I might hit the point very correctly, but I'm doing it quite slowly. So you have to do a trade-off. And that's where the engineering design process comes from. And where engineering thing is, you say, oh, this is my requirement, this is my environment, I want it to be able to go that straight, and so on. So let me do one more thing. It's still running. I show you. I don't know if you can see it. It's a little bit risky doing it on the table, but if I do it on the floor, you will not see it. So I get it moving. Get it moving, and now you see what I'm disturbing it, and you see how it tries to react to it? It tries to correct itself, and now when I hold my hand here, it will stop since it doesn't want to bump. So cool. So there's several programs running. One program running is just trying to get the wheels turning right, there's another program running which is a higher priority, which just checks that there's nothing there in front, so I don't bump it. Okay, so that's I only have like 3-4 more minutes. My point is, this method I also want to, don't be naive. What I mean with this is this. You all have, most of you, or nearly everybody here, or perhaps everybody has an MP3 player. Don't be naive. To explain you what an MP3 player is, you will need about 2 years of university hard mathematics. You know, products are incredibly complex. If you type a search name into Google and it comes back with a fraction of a second with an answer, believe me, they're not just looking in a phone book like this. They have sophisticated algorithms. For this algorithm, you would have to be already in grad school. So 4 years university plus another 1 or 2 years, and you have to be mathematically inclined to be able to understand it. Today, technology is so complex. The stuff you use daily, many people don't even appreciate it. And you're either using it or you're the one who's driving it. I think that's my time. So I hope to see you.